Welcome to Identifying Evil. I'm Bart. Whenever I attend a conference, it's always hard to know which talk to attend. Even after I choose, I'm never sure if the topics covered will be what I expect. So this is your chance to decide if this talk is for you. I'm going to spend a few minutes explaining why that you would want to spend the effort to learn reverse engineering skills, but then we'll get into the technical portions. Coming to these conferences, we see some really great talks. They cover things that we've never considered before, but they aren't always things that we can use in our day-to-day lives. We come from different roles and have different levels of experience. We have network admins, salespeople, students, coders, people from different backgrounds. I don't want anybody to feel left out, so I'm going to very quickly cover some basic material as we go along. But you can think of this as being like on a nature hike in a national park. We're not going to climb the mountain today, but we're going to jog to the foothills. So who am I? I've been using computers for 30 years, and I've been using them professionally for 20 years. My first computer was a Commodore VIC-20 with 3.5K of RAM, and I typed in the programs from the back of the Compute Gazette magazine and saved them on a cassette program. I don't have any special computer superhero skills. I just have a desire to help other people by sharing some of the things that I've learned. But I'm a defender. I think that being on the blue team is really cool. If you think about it, they make Bruce Lee movies because he's one person fighting off dozens of attackers at the same time. They don't make movies about being one of 200 ninjas that beat some poor guy to a pulp. But when you're a defender, you have an unlimited number of attackers that you've got to deal with using limited resources and limited time. But you don't want to interfere with the mission of the organization. It's almost like being told, here's a pair of chopsticks, go fight 200 ninjas and try to not get blood everywhere. But the first problem with dealing with ninjas is you have to realize that they're out there. You may see some things that are going on, but you don't really associate with ninjas. And ninjas, just like malware, can be incredibly difficult or almost invisible to see. But once you realize that you're dealing with ninjas, you have to come up with a battle plan. And if you're not sure of what a ninja is going to do or what they're capable of, you may design defenses that would stop you, but not a ninja. You just hope that they'll lose interest in you because you're so small, maybe they'll just go away and just leave you alone. But that's not likely to happen. And can you imagine having your entire incident response program be to haul everybody that's wounded and dead out and just bury them? I mean, you'd lose a lot of useful intelligence by not examining the dead and interviewing the wounded. But that's how a lot of companies deal with incident response. It's a lot faster to just re-image a machine, and rather than spend the time to understand what happened, why it happened, and what's behind it. But if you start looking at what is going on in your network, you can learn the tactics of the ninja. You'll start fighting back. And if you do your homework, you may just survive the next ninja battle. So why reverse engineer malware or other software? Well, we've talked about malware and breaches, but there are other reasons why you want to develop these skills. For example, grayware. You know, the other day I wanted a flashlight app for my cell phone. You know, it's one of these things, if you drop your keys in the dark, you just pull out your cell phone and turn on the camera light. I got ready to install it, and I looked at the permissions. They wanted access to my memory card, my network location, my contacts. Really? All I need access to is the light on the phone. It obviously was doing something that I didn't want it to do. Having reverse engineer skills can be helpful if you have undocumented software. Perhaps you've had a programmer that has left the company and you don't know where the source code is, but you've got to support this legacy application. Having some basic reverse engineering skills can help you support it, or in some cases change the functionality, like if you're wanting to use least user privilege, you'll know what resources it's trying to access. And then you probably should look at certification and accreditation of applications for high security environments. I know some of you may be thinking that, well, I avoid open source software. And if I stick with commercial stuff, no legitimate programmer would put a backdoor in it. Well, meet Ken Thompson. Some of you may recognize Ken as one of the original creators of Unix. And in 1984, the Association of Computing Machinery awarded him the Turing Award. His acceptance speech was later published in the Communication of ACM in August 1984 with the title of Reflections of Trusting Trust. And his acceptance speech was divided into 3 parts. In the first part, he told of a competition that he held with his buddies in college. And the goal was to create the smallest program possible that when compiled and executed would produce the source code to the program itself. In part 2, he discussed his work developing the first compiler for Unix. It was something of a chicken or egg problem in his words because it was compiling C and produce C. But the really interesting part was part 3. And he realized that he disclosed that every copy of Unix had a backdoor in it. It seems that when he was building the compiler, he put a backdoor in the source code and compiled the binary. He then removed all evidence from the source code, but the backdoor remained in the compiler. From then on, if you compiled a compiler with a compiler or anything else, the backdoor was included. What did the backdoor do? Well, when you got ready to log into a Unix system, you could put in your secret password, or you could put in Ken's password. In Ken's words, if you do not create it totally yourself, you can never really trust code. So before we get into the technical portions, there's a few last things that I'd like for you to keep in mind. Number 1, don't be a bull in a china shop. Have your computers configured to either quarantine or log any malware infections it finds. If you have it set to automatically delete, then you're losing a lot of valuable information. Realize that there's more than meets the eye. Your antivirus program may have found the black hole exploit kit within the browser cache of your computer, but it may have missed the Java dropper, it may have missed the PDF that was put on the machine, or the Zeus payload at the end. Take steps to protect yourself. Virtual machines are your best friend. And if you use the snapshot feature, it can really save you a lot of time, especially when you start tracing code. If you make a mistake, you can roll it back. I would encourage you to take other steps, such as changing the file extensions on file names. That way you can reduce your risk of accidentally triggering something. It's really stressful when you're trying to do some reverse engineering and you have to stop and do incident response on your own machine. Look beyond the mirages. One of the best ways to hide is to give a person exactly what they're expecting to see. You can put a piece of software out there that looks like an ordinary program, but it's really got Trojan functionality inside. When you start with reverse engineering, we hear a lot about encryption, and it makes kind of sound scary, like you may not have everything you need. But if the software can run on your computer, you have everything that you need to be able to decode it. When you get started doing a little bit of reversing, it can seem overwhelming, the amount of things that we have to learn. It's almost like trying to lift 300 pounds. But you want to start lifting 25 pounds, doing a little bit what you can, and build up from there. Then you can start working on the step steps. And finally, remember that it's easier to prove malice than it is innocence. The first 80% of malware is extremely easy to find, but the closer you get to 100%, the more difficult it gets. If your adversaries are sophisticated enough and they have enough resources, such as nation states, you may never find the malware. So let's start looking at the technical portions. Our time is valuable, so we want to leverage tools wherever we can to save ourselves time. The first stop on the path is VirusTotal. It scans computers, or it scans submitted software with 46 different antivirus programs, and you can submit a file hash or a URL for inspection. VirusTotal was purchased by Google the last year, and so they're getting some infusions of resources, and they've added sandboxing functionality. According to their blog, they perform sandbox analysis on Windows PE files that have not been previously seen, that are 8 megabytes or smaller, and on a best efforts basis. So reading that would lead me to believe that it doesn't examine the 64-bit PE plus files. So So you may want to look at other things than that. VirusTotal shares all the samples with the antivirus vendor, so you probably should not submit samples of your PDF document that has financial data or any trade secrets in it. Also realize that the bad guys will know that you submitted something, so you may want to submit a hash to it before you actually submit the malware. One problem with using VirusTotal is that it doesn't catch everything. I had to look at a Dell printer driver that was recognized by 3 out of 46 antivirus programs as being malicious. I had to reverse engineer it to verify that it was legitimate and it didn't have any extra features. By the same token, a lot of the malware I see today has about 3 out of 46 detections. So we've reached the point that the false positives are about equal with the true positives on malicious software. Submitting data to sandboxes can tell you a lot of information about what's been submitted. It can show you the files that have been created, modified, or deleted, processes started, any libraries that were loaded or functions that were called, registry keys that were accessed, and network captures. Some of these will actually pull a Windows PCAP so you can examine the message structure for your command and control systems. But VirusTotal Sandbox may not catch everything, so you may want to submit to some other public sandboxes. And there's some great ones out there, such as Threat and Track, which you may recognize by the old name GFI Sandbox. But if you don't want to share your information to public sandboxes, you can build your own. You've got the Cuckoo Sandbox and Buster, which make it fairly easy to create your own sandbox. You can use VMware or some type of virtualization product with your own tools to create your sandbox, or you can buy a pre-built one from ThreatTrack or FireEye or any of the other vendors. But let's talk about some sandbox evasions, because malware authors are constantly trying to defeat the sandbox developers. One tactic, when you have malware examining in a sandbox, you may not want it to be able to access the internet, because if it attacks somebody, you might feel like you're going to be held liable. So malware can check to see if it's got connectivity to a well-known site such as Google or MSN, or it can check something like, what is my IP? And the reason you would check what is my IP is to see if the IP address matches an antivirus vendor, or if it does not match the IP address space of the intended victim. So, to you defenders, you may want to look at your IDS systems to make sure you're looking for auto IP lookups. Also, when you're running things in a sandbox without network connectivity, you may have the primary payload, but if it downloads secondary or tertiary payloads, you may not get those. And then some malware will inspect the virtual machine that it's running on for drivers or software that's installed, registry keys, and if it sees something that may indicate that it's being debugged, it can change its behavior. Some of the newer malware will look for user activity such as key presses or mouse movement. And if it doesn't see that, then it just acts innocent. And then finally, you can use a timer that will give a delay. When you're processing with sandboxes, you're trying to submit so much data through there, you only have a limited amount of time to process a sample. So the malware author can delay long enough to hopefully avoid the analysis. So if you're not able to use a sandbox, you're going to have to resort to manual inspection. And I like to think of a hex editor as my X-ray machine that allows me to see patterns of invisible things within different files. Once you start using a hex editor, I kind of recommend opening various file formats and getting used to what is normal. If you're not familiar with hexadecimal, if you're not a coder or only programmed in higher level languages, you may not be familiar with hexadecimal. So just kind of a quick sidebar. With decimal, you count from 0 to 9, and then when you get to 10, you start a new column. But with hexadecimal, you count from 0 to 9 like normal, and then 10 through 15 uses the letters A through F, and then on 16, you start a new column. So hexadecimal 16 looks like decimal number 10. But getting back to looking at some of the normal documents that we see with a hex editor, a lot of times you'll see big sections of filler, such as 0 bytes, in this case of a Word document. An executable file on Windows will always start with the capital letters MZ, and there's usually a string of text a little bit later that says something like, "This program cannot be run in DOS mode." Well, this is an email that was received by HR. It's a resume. And when you look at it, it looks just a little bit odd. All those question marks where we should have zeros. Well, when I see that, the first thing that crosses my mind is XOR encoding. And there again, this is for people that have not done bit manipulation or coding. XOR will take a value and you can provide it a key. And if the values are the same, it will return 0. And if they're different, you'll return 1. So if you look at the middle column at the top row, you see a sequence of bits. If you look at the top row on the right column, you'll see that that sequence of bits can represent either the number 41 hexadecimal, the number 65 decimal, or the ASCII uppercase A. Well, going back to the middle, we can see the uppercase A, and I'm going to XOR encode it with a question mark. That will yield a tilde symbol. XOR encoding has an interesting property, is that if you XOR encode something twice with the same key, you'll get the original value back. In this case, I XOR encode the tilde with a question mark, and I get the capital A back. I realize that could be a little bit confusing, but there's an easier way. Stevens created a tool called XOR search, and I provided XOR search with a string to look for, and it found the XOR key of 3F for that resume type. Inside my hex editor are some functions that you can use that makes your life a lot easier, and this particular one had an XOR encoding function. So when I XOR encoded the Word document, I could see an embedded executable. If you delete everything before the capital MZ and save it to a file, you have a payload. How many of you have seen an email like this? Probably everybody. And we probably don't want to do that, right? We tell our users to not click on things that they're not expecting, but how do you validate things that they are expecting to make sure they're legitimate? What I use is the program that I released at DerbyCon last year called Spondulus. You could retrieve that link using Mozilla or wget, but other cases where you're following a link may require functionality such as posts that are only in Spondulus. So I request the link and I retrieve the HTML source code. When I start looking at it, I find that there are 3 JavaScript links that go to other websites. This is the hallmark of the Black Hole Exploit Kit. And in all 3 cases, they were compromised websites. If you want to be a good Samaritan, you could contact these people to know that they've got a problem. In this case, all 3 links led to the same place, but I have seen where they would go different places. The next hop was also a redirect to a compromised web server. So I used Spondulus to follow it again, and I found the Black Hole Exploit Kit landing page. What a mess. But you can decode that. All the instructions that you need can be searched, and if you scroll through, you'll find the decode instructions. Well, there's a couple of ways that you can decode it. One way is to create a script using something like Python or Perl and decode it. But a shortcut is to look for the word eval somewhere and replace it with document.write. Once you replace the eval with document.write and open it in the web browser, instead of actually executing the JavaScript, it'll print the code to the page. One word of caution though, if you do that, the bad guys know you're going to do that, and sometimes they will put a little extra feature in there for you. So beware of that. But once I've decoded the Black Hole Exploit Kit, I like to load it up into a text editor like Vim, where I can format it a little easier to see, and Vim has folding. And I can go through and see the various payloads that it's looking at. Now you may be thinking, well, this is a lot of trouble when I can just load this up in a virtual machine and go to the web page and see what happens. Well, that's true, but if you use a vulnerable machine and go to that website, then you're only going to get a specific payload. This will let you have full coverage of all the payloads that's being served by that landing page. You'll be able to see the individual vulnerabilities that are being looked for and the corresponding payload. Most of of the time, it'll be something specific to that version of software. But in this example that I have here, they all went to a PDF document. So I retrieved the PDF document using Spondulus, and I used a program called PDF Stream Dumper. PDF documents are comprised of multiple objects, and you can browse through the objects to look for shellcode or anything that looks kind of strange. And one of the objects I found was some obfuscated JavaScript. So I used the same techniques that I had for the other JavaScript, and I found a second layer of JavaScript obfuscation. Once I decoded that, I had a binary payload. Now this is an example where doing a little bit of search on the internet for Google or whatever can save you some time. I searched this on the internet and found a blog post by Brian Baskin where he pointed out the red serve command at the top that I might have ordinarily overlooked. I next downloaded the following payloads and submitted the hashes to virus total. Anybody care to guess what the detection rate was? 0. That's right, none of your antivirus would see it. So I got curious, how long will it take before antivirus detects it? So I waited 4 days and the second payload was detected with a 26 out of 46 detection ratio as one of the Zeus variants. The other payload wasn't detected, and so I submitted it and it turned out to be the Pony Loader Trojan. If you're not familiar with the Pony Loader, if you have an infected machine, it'll search your computer for all the credentials, such as email passwords, FTP passwords, and it'll upload it to an admin panel or command and control system. It has an interesting property in the way that it's encrypted, which is why it wasn't detected by the antivirus program. It embedded inside the executable is the individual URLs for the command and control. So it will encrypt 1 byte and then use that value as part of the cipher block chaining to encrypt the subsequent bytes. Since each phishing campaign can have a different URL, that's why your virus signatures don't work. So when I submitted this to VirusTotal, I got a sandbox report, and if you look at the top here, you'll see the URL that says Pony at the gate, and that's how the Pony Loader gets its name, because the pony's at the gate. Below that, you can see the other payloads that it's going to attempt to download, the DNS requests that it makes, and some of the TCP or UDP connections. But if you rely on just a sandbox report to get your indicators of compromise for your IDS or firewall, you may miss quite a bit. When I actually loaded it into a debugger and started tracing through it, I realized that it was trying to contact 4 control panels. Also, if you don't actually step through it with a debugger, you may not know why it has a default password list embedded, because the functions are not detected within the sandbox if the functions are never executed. So let's get back to a little bit of manual inspection. If you open up an executable within either Notepad, a hex editor, or one of the many strings programs, you can see embedded resources within the file. This is really handy if you're dealing with legitimate software and the programmer's left the company or whatever. You need to know what resources it's going to access. After that, you may want to load up the executable in one of the many PE viewer programs. Windows executable follows a known format called the PE file format, which means that the first 2 characters are always the capital letter MZ. A little bit later, you have a string that says this cannot run in DOS mode. And then you have various sections within the executable. It's traditional that you have a section for code, for data, and for resources. Malware authors will sometimes put secondary stage payloads within the resource sections, but legitimate programmers might put an icon for a Windows program within the resource. In addition to the various sections, you have something called the import table. Whenever a program is compiled by the developer, they don't want to create the work of art from scratch, so they're going to access external libraries, external DLLs. When they get ready to compile it, they can statically compile and link those executables. And that information is stored in the import table. It will list every DLL that's called and the functions within those DLLs. Once you actually execute the program, the loader will parse that import table to create something else called the import address table. They sound very much similar, but they're completely different. The import address table is a list of addresses that point to the addresses of the functions within the DLLs. Here's an example of loading up some executables within a program to pull out histograms. ByteHist is available for Mac, Linux, and Windows. On the left side, you see a histogram for a legitimate executable. In this case, it's SQLite, the binary. And it will show the histogram for the overall program as well as the individual sections. On the right, you see the histogram for the Pony loader. And you can see it looks dramatically different due to the encryption. I mentioned earlier that Windows executables can have the library statically linked at compile time. That information can be retrieved using a program called dumpbin. And when you're first learning the Windows API, this is a great tool. You can dump the imports of a known good program such as NSLOOKUP, and you can see what DLLs that it loads and the individual functions within those DLLs. I suggest that you also do that on the DLLs that are imported, and what you'll find is that some DLLs will import functions from other DLLs and turn around and re-export those. They do this for compatibility purposes. Just as a bit of a sidebar is if you dump the DLLs and the functions that are called, you can use that for automation by using Python C types or the Win32 API modules. This will let you call the individual system DLLs and use the scripting language as a glue. So let's talk about evading import function analysis. Obviously, if you're dumping the imports of something like Minesweeper and you see that it's trying to access your telephony functions or backup tapes, that might give you a clue that something's wrong. Malware authors know that you'll look at the import tables and they take steps to hide what they're doing. Instead of getting access to DLLs by statically linking them at compile time, they can use a delayed load or load them dynamically at runtime using load library and get proc address, which are part of the kernel 32 DLL. Malware authors will pack programs to try to compress them, save space, and also to mangle the import table to hide what they're doing. And there's several different hooking techniques that can be used. I had been to conferences for years and heard the term hook, but nobody had ever went to the trouble of explaining to me what a hook was. But basically, whenever you're calling a function within a DLL, if you replace the first few instructions of that function to point to your code, you can execute your code before you jump back to the original function. Another way is that you can modify the imported function within your own memory space. And then you can also overwrite the import address table to point to your function instead. Really advanced malware will use something called the process environment block. And basically the way this works is every thread that runs on your computer has to have certain information in order to run. And that's stored in the thread information block. Part of the thread information block is a structure called the process environment block. And the process environment block has to have environment variables and also information such as the DLLs that are loaded within a process. Well, you can search through the lower portion of the process environment block and you can find all the DLLs that are loaded within that process. Every Windows program has to have at least two DLLs that are loaded, NTDLL and kernel 32. So once you find the address of kernel 32, you can find the function's load library and get proc address, and at that point on, you can load whatever library you need. Now for a quick round of Intel assembly before we get into the debuggers. I'm going to describe this in the context of 32-bit processors such as the 8386. The 32-bit processors have four general purpose registers. There's the EAX, the EBX, the ECX, and the EDX. Although they're general purpose, they do have some specialized functions that are reflected within the instruction code. EAX is often used to pass values or temporary storage. EBX is used as part of an index for like a lookup table. ECX is used for counters and loops, and EDX is used for math operations or overflow. In addition to the general purpose registers, you have a couple of pointer registers. One is a source and one's a destination. Traditionally, you would read from the source and write to the destination. However, you can use them in the opposite way. Then you have two registers that are dedicated to the stack. You have the EBP, which forms one side of the stack frame, and it's generally set whenever you enter a function, and the ESP, which moves as you push and pop values from the stack and forms the other side of the stack frame. You may be wondering what a stack is. This is what I consider a stack. The classic definition of a stack is a dish plate stack like you have in a cafeteria. To me, that's a little bit confusing for how it actually works within assembly. I like to think of it as a storage shelf in your garage. Now, I don't know about you, but if I go to the storage shelf, the first place I'm going to put something is right here at eye level. The second place I'm going to put something is right below that, and I'm going to work my way down to the floor. Well, that's exactly how the stack works. You start at high memory locations and you work your way down. That may seem a little confusing, so I created, let's go to this part first. When you call a function, there are several different methods of doing that, several different conventions. But the most common will take the last argument and push it to the stack first, followed by the next to the last until you work your way to the very first argument. Then before you jump to the new function, you'll take the address of the next instruction and put it on the stack so you can return back to it. Once you get into the new stack, you'll want to save the old stack frame. So it's customary to push the EBP and then copy the current value of the ESP into the EBP. That's what's called the function prologue, and it'll help you recognize some functions. If you need local storage for that function, you'll subtract from the ESP to create the local storage. Whenever your function's done, you'll add back to the ESP, you'll pop the old stack frame back into the EBP, and then you'll jump back to the instruction following the call. And here's the handy-dandy diagram that I made. So you can see that with a function with 3 arguments, argument number 3 is on top, below that's argument 2, argument 1, and so forth. Now on the right side, you can see that any one of these values or memory addresses can be referenced using either the EBP or the ESP. In fact, malware authors will use them both ways to try to confuse you when you're going through your analysis. They'll create functions that have no purpose other than to line the stack frame up correctly. Intel assembly has 33 conditional jumps in addition to an ordinary jump. Which instruction is used depends on how the value that's being examined is treated, whether it's a signed or unsigned value. And whenever it does a comparison, that information is stored in the flags register, and that determines whether the jump is taken. I mentioned before that I was going to discuss assembly in context of a 32-bit processor, but to really get the big picture, you need to understand where we've been and where we're going. Back in the days of the 16-bit processor, such as 8286, the registers were known as AX, BX, CX, and DX. They could each have addressed independently. The bottom 8 bits could be addressed as AL, the upper 8 bits could be addressed as AH, and overall they could be referenced as AX. When Intel extended the instruction set to 32 bits, they put an E on the front. Well, they did the same thing when they went to the 64-bit processor, and they called it R8X. So with the 64-bit RAX register, you can access the bottom 32 bits as EAX, the bottom 16 bits as AX, the bottom 8 is AL, and bits 9 through 15 is AH. There were some other changes for 64-bit processors in that they added 8 new general-purpose registers, R8 through R15, and they added a new way to access the subcomponents of the registers. They also added the ability to index relative to the current instruction pointer. So here's some common examples of instructions. Whenever you see a disassembly listing and you see a number, that's in hexadecimal. So the very top example, we're loading the hexadecimal value 1000 into the register EAX. The instruction below that uses something called indirect addressing. And the value dead beef, instead of being loaded directly into the EAX, is going to be loaded into the memory address referenced by the value inside the EAX. In this case, EAX has the hexadecimal value 1000, so dead beef will go into the memory address hexadecimal 1000. I mentioned earlier how push instructions will place a value on the stack and decrement the stack pointer. And a pop will increment the stack pointer and copy the value back wherever you're going. So here's an example of putting these instructions into use. I want to find the string length. And so I set the ESI to point to the start of some string. And then I duplicate that into the EDI by using a move ESI to EDI. Now this third instruction is a little bit of a trick. Whenever I do a scan string instruction looking for a particular value, it's going to look at the value that's stored in the AL register by default. Now I could use a move AL, 0, which would put 0 in there. Or I could use move EAX, 0, which would put a 0 in there. But you'll often see an XOR function because, as we discussed earlier, when you XOR a value with itself, you'll get 0. It runs a little bit faster and it's a little bit shorter instruction. Next, we want a maximum loop count because we don't want to go into an infinite loop. So we load a really big number into the ECX register. Then we use the scan string, which will compare the value pointed to by the current instruction pointer against the value in the AL. As long as there's still a value within ECX, it hasn't reached the end of the limit, it will advance the pointer. Once we find the end, which is in the EDI register, we're going to copy that address into the EAX register, and then we'll subtract the value that pointed to the first of the string, which should tell us the string length. Now I'm going to show you a XOR encoding function. As I mentioned earlier, if you XOR encode something twice for the same value, you'll get your original value in return. So since we had the string length within the EAX register, I move it into the ECX for part of a loop. Then I initialize the ESI pointer to the start of the string, and then I grab that first byte, point it to it, and load it into the AL register. I do an XOR encoding, and then I store the value back out using the EDI register. And then the loop will continue to run as long as the CX register hasn't hit 0 yet. It's important to notice that values stored within Intel assembly are stored in least significant byte format. And that means that the hexadecimal value dead beef will have the value EF stored in the first byte, and the fourth byte would actually have the value DE. It's a little bit confusing, but when you start seeing these, you just have to be aware of that. This is a really good debugger, Ollie debug, and you can use this to trace through any malware. If you have enough patience and you're running in a virtual machine, you'll eventually crack whatever it is you're going through. In the upper left corner, you'll see the instruction pane where you can see Ollie's determination of what the instructions mean. Below that, you'll have the intermediate pane where you can see values that are about to be copied into a register or if a jump will be taken. Below that is a memory pane where you can watch memory as it's being changed. In the upper right corner, you have the registers, and whenever an instruction changes a register, by default, it'll set the type red, so you'll know that there's been a change. And below that, you can watch the stack as it moves up and down. When you're tracing through code, you have a couple of ways to do your stepping. You can do a step over or a step into. Whenever you're going into a user function, you'll want to step into it, instruction at a time. But if it's a library function or a function that you've previously documented, you'll probably save time by stepping over it. One word of caution, though, is if you're reversing something that is an interpreted language, such as a Visual Basic runtime, you'll actually have to step through it because there's a lot of action that goes through the individual functions. There's some really nice plugins available that can save you a lot of time. Malware authors will a lot of times create new memory sections and place code in that they have decoded or decrypted. And so Analyze This will help you analyze codes in these non-traditional code segments. Breakpoint Manager can allow you to export breakpoints that you set or import breakpoints. And breakpoints can save you a lot of time. You can set a breakpoint after a loop and let it run, and then when it hits the breakpoint, then you can kind of continue your stepping. Much easier than to go through a loop 1,000 times. Malware authors will use various anti-debugging tricks, and the Hide Debugger plugin can help defeat some of those. It won't catch all of those, such as the structured exception handling, or in some cases, but this will get you on your way. The last program I'm going to discuss is a little bit different from the other ones in that this is the first commercial program that I've discussed. IDA does have a free version, and it will do a dead code analysis. You give it an executable, and it will try to disassemble the code without actually executing it. It'll create a database that you can share with other people to look at a sample without having to share live malware. But if you do want to execute it, it does have a debugger built into it, and you can trace through the code. The nice thing about IDA is that it has a flow graph feature, and you can look at the code blocks and get an idea of how they interact. If you'll notice the bottom code block, it has a blue arrow that goes up to the top, and that indicates a loop. This next example would be an indication of a bunch of if statements or perhaps a case statement. You can see the ladder-like structure that reveals what's going on. Now, malware authors don't want you to disassemble their code or debug it, and so they have quite a few tricks to try to defeat analysis. We don't have time to go into a lot of those, but I do want to show you one that's fairly common. Whenever you have a jump, it's traditional that you would want to go to an address that ends in either 0, 4, 8, or C, and that's done for performance reasons. Now, they can put jump instructions in there and jump kind of off alignment, and when that happens, it can confuse the disassembly. So if you look at the top arrow, you can see that it's jumping to a memory address that ends in A. If you look at the bottom arrow, you can see that Ollie debug was confused and it has question marks. The instruction that's got the underline in it is where it was actually jumping. So here's how you can fix that. Within memory, you can replace that jump instruction with a not. And if you're not familiar, not stands for no operation, and it just basically fills space. Once you do that, then it's able to do the analysis correctly. We've covered a lot of ground. It's not everything that you need to analyze something like Stuxnet, but I hope it is something that can help you in your day-to-day jobs. Like I said, you can use it whenever you have a developer that leaves and you have lost the source code, or grayware, or whatever. If you have any questions, I can be reached here. Here's my contact information. Any questions? Yes?
In an attempt to not let your in and out, do you have malware recommendations that I can definitely
And the question was, in an effort to avoid lifting 300 pounds, do I have any recommendations of malware that you can get started on? Is that correct? I would suggest looking at your inbox, your spam folder. You'd be surprised what you find in there. But there's some great sites too. VirusShare, I think you can sign up for an account and they'll vet you. They have several terabytes of data. Dave Marcus gave a talk earlier in the day, and he said that if you had samples that you created Yara for, that he would provide samples with. But malware's not hard to find if you just start looking. Yeah, go to a porn site. Yes?
They really should start by looking at their operating system files before they dig into real malware. That gets them a little bit more used to it in a benign way.
Well, the comment was that you should probably look at the operating system files before you start looking at malware, because it's, as I understand, a little bit safer to operate on and hopefully benign. That's true, assuming that your operating system's not infected with malware. But yes, that's probably the safest way to get started. And like I said, when you start dumping the DLLs, you know you want to take advantage of that for scripting purposes. Yes?
Two things. The practical malware analysis book is a starting place because it has stats and exercises that if we're not to some extent. And also, I have a question. When analyzing malware, in your opinion, do you think it's helpful to, instead of looking at instructions and trying to figure it out, do you think it's helpful to instead of looking at blocks of code and kind of recognize patterns or to see what it's doing?
Yeah, the question, the remark first was that Practical Malware Analysis is a great book, and I certainly agree. It does have some great examples and tutorials on how to analyze it. And I think your question was, is it helpful to actually execute the code in a safe environment to get an idea of behavior so that you can save some time?
Well, is it helpful to sort of recognize patterns within the code that you're trying to analyze instead of trying to look at to figure it out?
Yeah, I would recommend trying to have a high-level approach first. Try to use automation as much as possible and get the big picture. And only when you need specific detail about a specific section, go through and actually trace it. Other questions? Thank you for your time, and I hope